Scientists reveal how our solar system could capture a new planet. When Umama traversed our solar system in 2017, it was the first confirmed interstellar object, ISO, to do so. And then in 2019, comet 2I Borisov did the same thing. And these are the only two confirmed ISOs to visit our solar system that we have seen. There may have been more that we didn't see, right? Now, many more ISOs must have visited our solar system's long history, and many more will visit in the future. There are obviously more of these objects out there, and the upcoming Vera Rubin Observatory is expected to discover many more. It's possible that the Sun could capture an ISO or a rogue planet in the same way that some of the planets have captured moons. It all comes down to phase space. And what would happen to our mature, sedate solar system if it suddenly gained another member? That would depend on the object's mass and eventual orbit that it found itself in. It's an interesting thought experiment. While Borisov and Umama were smaller objects, a more massive rogue star joining our solar system could generate orbital chaos. It could potentially later alter the course of our life on Earth, although that is highly improbable. How likely is this scenario? A new research note in Celestial Mechanics and Dynamics Astronomy outlines how our solar system could capture an ISO. It's titled Permanent Capture into the Solar System, and the authors are Edward Bell Bruno from Department of Mathematics Sciences at Yeshiva University and James Green, formerly of NASA and now from Space Science Endeavors. Phase space is a mathematical representation that describes the state of a dynamical system like our solar system. Phase space uses coordinates that represent both position and momentum. It's like a multidimensional space that contains all of the possible orbital configurations around the Sun. Phase space captures a state of dynamical systems by tracking both position and momentum characteristics. Our solar system's phase space has capture points where an ISO can find itself gravitationally bound to our Sun. Phase space is complex and is based on Hamiltonian mechanics. Things like orbital eccentricity, semi-major axis, and orbital inclination all feed into it. Phase space is best understood as a multidimensional landscape. Our solar system's phase space includes two types of capture points, weak and permanent. Weak capture points are regions in space where an object can be temporarily drawn into a semi-stable orbit. These points are often where the outer edges of objects' gravitational boundaries meet. They're more like gravitational nudges than an orbital adoption. Permanent capture points are regions in space where an object can be permanently captured into a stable orbit. An object's angular momentum and energy are an exact configuration that allows it to maintain an orbit. In planetary systems, these permanent capture points are stable orbital configurations that persist for extremely long periods of time. Our solar system's phase space is extremely complex and involves many moving bodies and their changing coordinates. Subtle changes in phase space coordinates can allow objects to transition between permanent capture states and weak capture states. By the same token, subtle differences in ISOs or rogue planets can lead them into these points. In their research notes, the authors describe the permanent capture of an ISO this way: the permanent capture of a small body P about the Sun's S from interstellar space occurs when P can never escape back into the interstellar space and remains captured within the solar system for all future time, moving without collision with the Sun. Purists will note that nothing can be the same for all future time, but the point stands. Other researchers have delved into the scenario, but this work goes a step further. In addition to being permanently captured, P is also weakly captured, they write. It revolves around the notoriously difficult to solve three-body problem. Also, unlike previous research, which uses Jupiter as a third body, this work uses the galaxy's tidal force as a third body along with P and S. This tidal force has an appreciable effect on the structure of the phase space for the velocity range and distance from the Sun we are considering, they explain in their paper. The paper focuses on the theoretical nature of phase space and interstellar object capture. It studies dynamical and topological properties of a special type of permanent capture called permanent weak capture, which occurs for infinite time. An object in permanent weak capture will never escape, but will never reach a consistent stable orbit. It asymptotically approaches the capture set without colliding with a star. There's not much debate that rogue planets exist likely in large numbers. Stars form in groups that eventually disperse over a wider area. Since stars host planets, some of these planets will be dispersed through gravitational interactions prior to conatal stars gaining some separation from one another. The final architecture of any solar system will be shaped by planet-planet scattering in addition to the stellar flybys of the adjacent forming star systems, since close encounters can pull planets as small bodies out of the system, creating what are called rogue planets, the authors explain. When taken together, planet ejection from early planet-planet scattering and stellar encounters, and in the subsequent evolution of the multi-planet solar system, should be common and supports the evidence for a very large number of rogue planets that are free-floating in interstellar space that perhaps exceed the number of stars, the authors wrote, noting that that assertion is controversial. So what does all this add up to? The researchers developed a capture cross-section of the solar system's phase space, then calculated how many rogue planets are in our solar system's vicinity. In our solar neighborhood, which extends to a radius of 6 parsecs around the Sun, there are 131 stars and brown dwarfs to a radius of 6 parsecs around the Sun. Astronomers know that at least several of them host planets, and all of them may very well be host planets we have not detected yet. Every million years, about 2 of our stellar neighbors come within a few light years of Earth. However, 6 stars are expected to closely pass by the next 50,000 years, the authors wrote. That's news to me, and that, I mean, the hair is standing up on my head. That's very close. 6 stars expected to closely pass by in the next 50,000 years, right? The Oort cloud's outer boundary is about 1.5 light years away, so some of these stellar encounters could easily dislodge objects from the cloud and send them towards the inner solar system. This has already happened many times, as the cloud is likely the source of long-period comets. The researchers identified openings in the solar system's phase space that could allow some of these objects, or ISOs, or rogue planets, to reach permanent weak capture. They're opening the Sun's Hill sphere, a region where the Sun's gravity is the dominant gravitational force for capturing satellites. These openings are 3.81 light years away from the Sun, in the direction of the galactic center or opposite to it. Permanent weak capture of interstellar objects into the solar system is possible through these openings, the authors state. They would move chaotically within the Hill sphere to permanent capture about the Sun, taking an arbitrary long time to infinitely many cycles. These objects would never collide with the Sun and could be captured permanently. A rogue planet could perturb the orbits of our planets. That may be possible to detect, they conclude. They're still in the early days of understanding ISOs and rogue planets. We know they're out there, but we don't know how many or where they are. The Vera Rubin Observatory might open our eyes to this population of objects. It may even show that they cluster in some regions and avoid others. According to this work, if they're close to any of the openings of the Sun's Hill sphere, we could have a visitor that decides to stay. This was originally from Universe Today by Evan Go on Science Alert. Please leave your comments and thank you for your support. support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.